80,000 pounds. That's the legal maximum weight for a fully loaded semi-truck on highways in the United States. To put that into perspective, it's roughly equivalent to 6 adult African elephants, a compact naval patrol vessel, or a fully filled commercial swimming pool. And every single pound of that mass must be transferred downward, through the truck's frame, along the axles, and ultimately into the pavement beneath its wheels. Here's the part most people overlook. The real challenge isn't the engine, the cargo, or even the driver. It's the road itself. Once you grasp that, the reason a semi-truck has 18 wheels stops being just a trucking question. It becomes about physics, road design, and a federal regulation that quietly shapes every highway in the country. By the time we're done, you won't see a passing semi the same way again. Most people hold a simple assumption. More wheels mean more traction, better grip, improved control on wet surfaces, and greater stability through turns. It sounds reasonable. It feels intuitive. It's the kind of explanation that feels complete, easy to accept, without digging any deeper. But it's largely misleading. Traction does matter, but it isn't the reason behind this design. A truck could achieve sufficient grip with far fewer wheels. The real issue is something most drivers rarely consider, even though its effects are all around them every day. The issue is ground pressure. Imagine a woman wearing high heels standing on a hardwood floor. She weighs about 130 pounds. That entire weight is focused onto a heel no larger than a pencil eraser. The force at that tiny point becomes extremely intense, strong enough to mark the surface or even crack weaker materials, not because she's unusually heavy, but because the load is concentrated in one small area with nowhere to disperse. Every pound is pushed into a single spot. Now imagine that same person lying flat across the floor. The weight hasn't changed. The body is the same, but the result is completely different. The floor barely registers the impact. The force itself hasn't changed. What changes is how that force is spread out. Distribution is what matters. A truck interacts with the road in exactly the same way, just on a much larger and more destructive scale. Under the right conditions, that force can damage reinforced concrete and even deform steel bridge structures, often without an obvious cause at first glance. If a single axle were forced to carry the full 80,000-pound load, the road wouldn't simply wear out over time. It would break down rapidly. The pressure would be focused into a small number of contact points, causing the surface beneath to bend, crack, and eventually fail, not over decades. In some high-traffic freight routes, the damage can show up within months, as the same heavy loads roll over the same stretch of road thousands of times each week. The fix follows the exact same idea as spreading your body across the floor. Distribute the load. More wheels, more axles, and greater spacing between them allow the weight to be shared across multiple contact points. The total force doesn't change, but its effect does. And here's the part that surprises most people the first time they hear it. A fully loaded semi-truck tire, carrying only its portion of that 80,000-pound load, can actually apply less pressure per square inch to the road than a typical passenger car tire parked in your driveway. Lower, not higher. When you break it down by each point of contact, the massive truck is actually gentler on the road than a typical family car. A standard passenger vehicle tire usually supports around 1,200 to 1,500 pounds across its contact area. By contrast, a fully loaded semi-truck tire, designed to be wider, run at higher inflation pressures, and share the load with many other tires, distributes its portion of the weight far more efficiently, often falling in the range of about 100 to 110 pounds per square inch. The larger vehicle ends up being less aggressive on the pavement than the smaller one, but only because its weight is spread across enough tires to make the numbers work in the road's favor. That's the real reason this design exists. Not for traction, not for appearance, and not out of tradition, but because of the unavoidable physics of ground pressure. It's a constraint engineers have to respect, and one that road surfaces simply can't handle without proper load distribution. And this is where things become very exact, because it's not just about physics, it's also written into law. Since 1975, the United States has enforced a regulation known as the Federal Bridge Formula, which directly shapes how weight is distributed across truck axles on public highways. It's one of the most influential pieces of engineering policy that most people have never even heard of. Yet, it quietly determines the design of every commercial truck on the road. It doesn't just set a limit on total weight. It dictates how that weight must be spread across axles, and even how far apart those axles need to be positioned. The reason behind it comes down to bridges. A bridge isn't evaluated solely by the total load a vehicle carries. What truly matters is how concentrated that load becomes at specific points as the vehicle moves across it. A vehicle that concentrates its entire load on just a couple of closely spaced axles places a very different kind of strain on a bridge compared to the same weight distributed across multiple axles spread further apart. The force becomes more focused, more abrupt, and significantly more damaging to the structure beneath. Move that same cargo across a bridge with poor axle spacing, and it's not just a regulatory issue. You're placing real stress on the steel and concrete that keep the structure intact. The 18-wheel layout is essentially engineered to comply with the federal bridge formula while handling the most common freight weights and trailer lengths. Typically, there are 3 axle sets under the tractor unit and 2 more toward the rear of the trailer, each sharing a defined portion of the total load within legal limits. The distances between these axles are not arbitrary. They are carefully calculated to keep the stress placed on bridges within acceptable levels at every point along the crossing. Take away axles or wheels, and the weight becomes more concentrated. Once that concentration increases, the result is immediate: higher road damage, unsafe bridge loading, or a direct violation of federal transport regulations. Often, all 3 consequences appear at once. Now track the truck in real conditions, not as theory, but as something moving through roads you've likely driven on. A fully loaded Freightliner Cascadia leaves a distribution hub near Louisville, Kentucky, merging onto Interstate 65 with a full retail shipment. Behind it, a 53-foot aluminum trailer carries freight at the legal limit, with pallets stacked tightly from front to back and carefully balanced across the floor before the doors are sealed. The 5th wheel coupling links the trailer to the tractor at a carefully engineered point designed to divide the trailer's load between the rear trailer axles and the truck's drive axles. That position isn't a matter of preference or ease of hookup. It's dictated by strict weight balance requirements. Shift the coupling too far forward, and too much load transfers onto the drive axles. Push it too far back, and you risk overloading the steering axle, creating unsafe handling conditions and potential structural strain. This balance has to be engineered correctly before the truck even rolls out of the yard. Once it reaches open highway speeds, the load is never perfectly static. It subtly redistributes with every slope and gradient in the road. On a long uphill stretch through southern Indiana, more force shifts toward the trailer's rear axles. On the way down, that balance moves forward, increasing the burden on the steering axle. The tires don't just roll through these changes. They actively absorb them, showing the effect as heat buildup and sidewall flex. From the outside, nothing looks like it's changing. But at 70 miles per hour, each tire is constantly responding to shifting loads in real time. And there's one detail most people never stop to think about, yet it completely changes how you see every truck you pass. Those 18 wheels are not all performing identical roles at the same instant. The paired tires you see on the drive and trailer axles, often mounted side by side on a single hub with only a small gap between them, are known as duals. Their purpose isn't simply to increase grip. Instead, they split the concentrated load and act as a redundancy system in case one tire gives out. If one of those dual tires suddenly fails at highway speed while hauling a full 80,000-pound load, the remaining tire in the pair immediately takes over the burden. This is what helps prevent an abrupt loss of control or a violent lane departure, keeping the truck stable enough to continue safely down the road. The load doesn't immediately collapse onto one unsupported point that cannot cope with it. Instead, the remaining tire in the pair picks up the slack, giving the driver a brief but critical window to react and maintain control. That built-in tolerance isn't incidental. At highway speeds, under full freight, a single tire failure without a paired backup is far more than a mechanical issue on the roadside. It can quickly escalate into a dangerous sequence of instability, if not managed immediately. This paired setup also has an effect on the pavement itself. Two narrower tires running together create a broader combined footprint than one single wide tire carrying an equivalent load. More surface area in contact with the road means the pressure drops per square inch. The equation always circles back to the same principle: distribute the load, preserve the pavement, and remain within legal limits. The 18-wheel setup isn't a universal standard carved in stone. It's simply one of many regional solutions shaped by infrastructure limits and regulations. Across Europe, freight combinations use different axle layouts, tuned specifically to their road strength classifications. In Australia, massive road trains stretching over 50 meters operate with wheel and axle counts that would be completely non-compliant on U.S. highways. Same physics everywhere, different rules, different engineering responses. The wheel count on a truck isn't a universal design choice. It's a response to a very specific set of constraints shaped by national laws, infrastructure limits, and engineering standards. Different countries, different bridge ratings, and different road durability standards all produce different configurations. If the regulations shift, the axle layout shifts with them. The vehicle itself isn't the fixed element. The governing rules and the infrastructure those rules are designed to protect are what drive the design. In practical terms, every 18-wheel truck moving through U.S. highways is effectively a rolling compliance system. Its structure is engineered around legal requirements, built directly into the frame, ensuring that weight distribution, road impact, and bridge loading all stay within allowable limits. This layout is not simply the result of physics alone, but also of federal bridge rules and state-by-state weight restrictions working together with real-world engineering limits. No one chose 18 wheels because it felt optimal or visually balanced. Instead, engineers reverse-engineered the design from legal constraints, roadway durability, and bridge load capacities until they arrived at a setup that balances freight efficiency with compliance and infrastructure safety. The goal was always a compromise: maximize how much cargo can be moved, stay within legal limits, and reduce long-term damage to roads and bridges. But there's still one more layer, something rarely discussed outside logistics and transport engineering, that ties everything together in a way most people never consider. Axle limits aren't only about safeguarding highways and bridge structures. They also act as a form of protection for the vehicle itself. When an axle is pushed beyond its rated capacity, the impact isn't confined to the ground below. It spreads through the entire mechanical system. Excess load increases strain on wheel bearings, heats up brake assemblies, overloads suspension components, and places additional stress on the frame structure all at once. A truck that repeatedly operates above its axle specifications isn't just in violation of regulations. It is actively speeding up wear across every part connected to the load path. Wheel bearings, in particular, begin operating at higher temperatures than they were designed to sustain. Suspension bushings begin to degrade more quickly. Brake parts experience uneven wear patterns. Frame members can develop localized stress points in areas never intended to handle sustained loading. The 18-wheel arrangement is effectively balanced so that every part of the system, from the wheel fasteners at the hub to the leaf springs supporting the V-chassis, operates within its intended stress envelope over the vehicle's service life. Remove axles from that equation, and the remaining ones don't simply take on extra weight. They accumulate damage at a faster rate, become more expensive to maintain, and reach failure conditions earlier, often in the most inconvenient and high-risk situations, far from any controlled environment. So the next time a fully loaded long-haul semi-truck rolls past you on the interstate, you're not just looking at a single design choice. You're seeing a standardized engineering response to the same set of constraints across the entire industry. That kind of configuration isn't unique to one manufacturer. It shows up across many Class 8 highway tractors, including models like the Kenworth T680, the Freightliner Cascadia, the Peterbilt 579, the Volvo VNL, and the International LT series. Different badges, different cabins, different styling, but the same underlying logic. Axle spacing, wheel count, and load distribution are all converging toward the same solution because they're all solving the same problem under the same laws of physics and highway regulation. What you're actually observing isn't a design built around extra grip or inherited convention. It's the end result of engineering decisions driven by limits in road durability, bridge loading capacity, and a regulatory framework introduced in 1975 that still influences how commercial freight is configured today. Each truck is essentially shaped by those boundaries, with its wheel layout reflecting a balance between what highways can endure, what bridges can safely carry, and what the law permits at scale. The total mass remains the same, but what changes is how that force interacts with